Good afternoon. Wow, I see the attendance is a little bit sparse today, but you are here and that's what's important. I thank you for coming. It's a holiday weekend, so that's to be expected. The last time I started with a chem quiz, which was a midterm bonus question, and I asked you this question here, and I have to correct myself. Not that I did what I said what I did was wrong, but I didn't see the obvious, okay? The question was, which energy level diagram corresponds to the observed spectrum? And I said, none of the above, and the explanation I gave to you was actually right. But there's two solutions to that problem, okay? And the right solution is D. And if you look at D, so you have these three levels. You have one, you go from this level, so this is the difference in energies, okay? It's the difference in energy. You go from a very high level to a low level, okay? And this is a very high energy. That's from this level to this level, I get this emission line here. That's a very high nu, okay? High energy. Yes, sir. You would get, if you put D, you will get the extra points, okay? And if you would put D in your midterm, you also get the right point, all right? So, now, didn't you get my email? Okay, everything is in there, all right? The extra points are not there. They will will be posted extra. But the points for your midterm, they are correct because we only posted them once. After we figured this all out, we posted them, okay? So now there's a second one here, which is a second less energy, but it's a pretty high energy still. It goes from here to here. This is this difference, okay? And delta E is smaller than this, but larger than this. So this is this one here. And the third one, it goes from here to here. That's the smallest energy. The energy difference is small. So this would be that one. And I could actually draw this in reverse, as I did, and I explained it to you. It would be also true. Yeah? Okay. So let's settle down. Yes, ma'am. No. C, you have this. Oh, let's go for C then. So you have 1, 2, 3, 4. Would that be here, that one? It should be in the middle. It should be 1/3. Okay? This would have to be in the middle of this here if you have C. All right? Because the distances have to be 1/3, 1/3. Okay? All right. So with this, we have the answer D. I cleared the confusion. And now we're going to go to our regular lecture. I think this midterm was extremely well with all the bonus points I'm giving you. Gee, my God, you have probably over 120 points. All right? So, but this sometimes happens. So the next time we will see that this doesn't happen. Yes, sir. If you get in this and D, you get an extra midterm bonus. There will be a column. It will have 3 points in there.
So if we got right on the midterm and the final,
you get extra 3 points. Yeah. Yeah, you get, no, you have the midterm has the points, okay? And then you get the bonus points, they are extra. The bonus points if you answer the question correctly, yes?
You said for the midterm you guys already put the points?
Beg your pardon? No, in the midterm, if you have it right, you get the midterm points, whatever it is. And then you have the bonus question, it's separate from the midterm. You get these extra points.
You already added the ones for the midterm.
In the midterm is fine, but the bonus question is not posted yet, okay? But the midterm are the final scores. All right? So is this clear now? Can I go on now, please? All right. You know now that how to fill orbitals. And if I can have your undivided attention, that would be even better. So you know how to fill orbitals with electrons. You know that if you have degenerate orbitals of the same kind, for example, 2px, 2py, 2pc, you fill them first with parallel spin, and then you start filling them antiparallel. And we talked then, so you can now essentially determine the electronic configuration of anything in the periodic table, with some few exceptions, all right? You may have read some of them in the book. Now, today, we're going to continue about the periodic table, and the periodic table was founded by Mendeleev, and he had 60 somewhat compounds that he compared the chemical behavior of these compounds to each other, and with this he came up with this periodicity, that periodic table, which he formulated like this, and it looks pretty much like the periodic table we do have now. We have more than 63 elements. We have 112 so far that are being approved by the IUPAC, and so this is quite some time ago. So we were pretty busy to finding new elements. So you know now that in the periodic table you go from left to right, and this is the main quantum number. And we call this a period. Period 1 is main quantum number 1. Period 2, main quantum number 2. Period 3, main quantum number 3. And so on till we get to the 7th period. And this is, I hope I don't hit Karen here, the main quantum number 7. All right? So you know now how to fill this. You know how this all behaves. And if you go down from top to bottom, what you see here, for example, this is the same group here, okay? Group 1, group 2, group 3, 4, 5, 6, till you get to group 18, and you look in one group here, you notice that you start out, when you start in the next main quantum number, with the same orbital configuration. You start with s orbital here, and this here, you have an s1 configuration. Nevertheless, the one here it's 1s1, here it's 2s1, 3s1, until 7s1, so you are much further out with the orbitals in space, but you have the same outermost electronic configuration, and this is called the valence electron configuration. And so because you have s1 configuration here, and because the outermost orbitals, or the electrons in the outermost orbitals, are involved in the binding, so you have very similar behavior, or somewhat similar behavior, when they start binding. And you could, here for example, and even not only when they start binding, also sodium, potassium, and rubidium, for example, they have similar behavior, somewhat similar behavior. And we talk about some of these behaviors today as it pertains to the elements itself. So we have here, and this would be the S2 homologues here, or the S2, down here the group 2 would be S2 group, and then you have, would be the same, you have S22, and then you have P1 here. This would be P1, P2, P3, P4, P5, P6, all right? But you have to add the quantum number in front of there. And we know generally these are the alkali metals here, these are the alkaline earths, and the metallic character of these metals here increases if you go from top to bottom. So hydrogen is not a metal, we know that, but we know that sodium is a metal, and potassium behaves even more as a metal, and so on. So the metallic character increases as you go down. It decreases as you go from left to right. We have here the transition metals, and we have here the metalloids. They are between metals and non-metals, or they are called poor metals here in this case. And then we have the non-metals, okay? And so the metallic character decreases from left to right and increases on the left side of the periodic table, where you have the metals, from top to bottom within the group. So this is called the S block here. This would be the P block. This would be the D block. And then we have a new block which starts here in the 6th period. These are the 4F electrons. So these are after lanthanum. Lanthanum is element number 57. And after that, we start filling the 4F electrons, the lanthanides. And then after element number 89, which sits here, we start filling the actinides up to 103. And then we go back into the transition metal group. All right? So you know now the architecture of the periodic table, at least to some extent. And we will talk a little bit about ionization energy and electron affinity. And you remember I had a demo here with a volunteer. I was a nucleus, and I was hanging on to my electron. And then that your colleague tried to take that electron away from me, and it showed to you that in order to take an electron away from an atom, you need to put in energy. So you have to put in energy that that electron gets away from the nucleus, from the charge of the nucleus, because the electron is negative, the nucleus is positive. So there is a Coulomb interaction, an attractive force, and I have to overcome that attractive force. And in order to overcome that, which is also energy essentially, in order to overcome that, I have to put in energy and rip off that electron. Okay? And whenever I put in energy, we have a positive sign for the energy. When you put in energy in a system, it's positive. All right? Now, this was the case here. This was the ionization. And we have the ionization energy, and this is a positive value because we put in energy. We need to rip it away from the nucleus, that electron. And now, if we go, for example, let's say this would be a 1s electron compared to a 3s electron. Which one would be easier to ionize, the 1s electron or the 3s electron? If you go, for example, 3s would be sodium. Would be hydrogen or sodium easier to ionize? And why is that? You say sodium, this is correct. And why is that? Because you have a shielding effect. Yeah? You have a shielding effect, and this shielding effect, the effective charge on that electron, the effective positive charge, is not the full nuclear charge. It's smaller than the full nuclear charge because you have the other electrons, they are also attracted by the nucleus. And so the further and further you go out in orbitals in the same group here, in the same group, the easier it is probably to ionize that. All right? Now, the opposite is the addition of an electron to an atom. So I showed to you when you add an electron to a fully balanced, electronically or electrically balanced atom, so it comes in and it releases energy. So this is generally the case when you form bonds. When you put two things together, you form bonds. You always release energy. I will say this 100,000 times to you probably. And this is the same thing. You form a bond between the electron and the nucleus, so you release energy. Okay? And this is called the electron affinity. And the electron affinity is a negative number because you release energy. And always, when you put in energy in a system, it will be in green, and when you release energy, it will be in red. I didn't do it red here because it doesn't show very well on the web. Red, you don't see anything on the web. So now, what I just said to you is if I go from sodium to potassium to rubidium, you should see that the ionization energy for sodium is much higher than for rubidium, and potassium is in the middle. As we go within the group, we go down. We have the same valence electron. This would be the S1 electron. It's much easier to remove. Not much easier, but it's easier to remove as you are in the higher quantum number. And this would be the sodium would be the 3s, potassium 4s, and rubidium the 5s. All right. So we would have then a sodium plus, a potassium plus, and a rubidium plus. And you need 496 kilojoules per mole to rip that electron away from a sodium atom, from a neutral sodium atom, but only 403 kilojoules per mole to rip this electron from rubidium. Okay? Now, the ionization energy, they have not a whole lot of, not very much affinity to form negative ions. Okay? The ionization, the electron affinity, EA. This is the electron affinity. So that's a negative number, because if a neutral atom adds an electron, we release energy. So, but they have not a very strong tendency to attract electrons. So they don't want to be anions, really. But if you go over to far in the right side here to the halogens, these are the halogens, chlorine and bromine and iodine, they have these much larger electron affinities. So they like to be very much having a negative charge. You see how difficult it is to rip an electron off of them here, the ionization energy is huge compared to this here. So, but they have this relatively large electron affinity. So Cl minus is a very likely possibility. Br minus is a possibility, and I minus is a possibility. What is pretty difficult, making a Cl plus and a Br plus and the iodine plus, okay? That would be iodide plus, because you need these huge energies to rip off that electron. So let's do an experiment and let's talk about it. We can set up the experiment if Karen would be here. I explained to you metals react with water. Most metals react with, of course, iron doesn't react with water, it rusts. But we want to see a real reaction. So let's take the alkali metals here. Let's take some of them. Let's take lithium, sodium, and potassium. Now we know now that what they do, they ionize, okay? And the ionization energy gets smaller if we go down within the group, all right? So I know also that water, if I give it some electrons, it gets reduced to hydrogen and OH minus, hydrogen gas and OH minus. And if you throw these metals, these specific metals into water, the water will pull off that electron from them, all right? And with this, if this is a relatively large exothermic reaction, and this is an endothermic reaction, we have to put in energy, right? So this reaction will always have the same energy balance. It will give off energy, yeah? But this reaction, we have to put in energy. Now, if I have lithium, or if I have rubidium, I would have to put in less energy to ionize the rubidium than for the lithium. Does this make sense? Okay. So if I throw lithium in water, then I take a lot of the energy that this liberates to rip that electron off from here, and the rest of that energy you would see released. But if I, for example, use rubidium, I need a lot less energy. So if this energy is always the same here, then I would release more energy. Let's see if this is true. So we need shields here. I put this up, you put the back up. Oh, with my back, I can't do that. All right, good. So you already get the hang of it. This is an exothermic reaction because we have shielding there. If energy is released of a system, we always put up shielding to protect us and to protect you. If the system sucks energy from the surrounding, okay, if we have to put in energy, then we never put in up a shield because there's so much energy in this room, especially with you here, there's so much energy in the room that it doesn't make a big difference if we have a little chemical reaction, if the energy comes from the surrounding, okay? So we have, if I could have that picture up there, please. Good. So you have a trough with water. So there we want to make hydrogen. Hydrogen and what was it? Hydrogen and, let me see that 1 second here. Hydrogen and hydroxide, the metal hydroxide. So you make hydrogen here and the hydroxide which forms the metal hydroxide. So let's start out with lithium. Maybe you can turn the light down a little bit. And so lithium is under, you see, where's the lithium? There's the lithium, you see it here? See any gas bubbles there? Yeah, there are gases released. What is that gas? Hydrogen. But it's a very mellow reaction. Not much going on. There's some energy released, obviously. Yeah, I see there's a little bit of energy released, but for this we don't need that shield. Don't worry, I tell you when it's there, okay? All right. I'm the first one to protect myself. So there it is. Yeah, it's a pretty mellow reaction. It's an exothermic reaction. There you see the hydrogen gas, and you see a little bit of energy released. Because we need so much energy from making the hydrogen that we free, in turn, we need that energy to pull off that electron from the lithium. Now let's do sodium. What should we see? It's the same reaction with forming water to hydrogen, but the reaction that is different is now that we have sodium, and sodium, that electron is less tightly bound, so I need less energy to pull it off, and with this, the total reaction should have more energy released. Okay? Let's do now sodium. There it is. Okay. Oh. See, there's forms some kind of a sphere, and it's bubbling. It moves faster, a little faster. So where is the energy, please? There it is. Okay. Come on. Do something. There it is. But it's a little more vigorous. There you see, aha, there was something. It's a little more vigorous. Obviously, hydrogen bubbles get trapped, and then they release them, and then they maybe have a little fireworks there. So that's pretty mellow at times. But there is a little bit more energy released than in the previous reaction. Okay, that's a floater. All right. What an excitement. Good. This morning it did a little better. Next time you put a lot more in there. But it takes forever then to dissolve it. So what we are making, this will be, the water will become basic. So it will have a metal hydroxide dissolved in there. OH minus will be basic pH. Okay. So, all right. What happened? You set the timer for that thing? That didn't take that long this morning, isn't it? And it was more vigorous. It's the moisture. So these compounds, they are sensitive to oxygen and to water. So we have to store them in oil, because if you let them sit on the bench, they will react immediately with the moisture of the air. And there it's gone. Now let's see. If we put in potassium, I think we should get some more reaction. Let's try that. I would like to put in rubidium, but this is very expensive and it's very violent, okay? Because it's very easy to take that electron. Let's go and have rubidium. Oh my God, see that? See that? You have another piece? No? Okay. All right, good. Thank you, Karen. You get the drift, okay? And this was the reaction of alkali metal with water, where we show you the ionization energy difference. So you can also have successive ionization energy. You can take off the first electron. This, for example, aluminum. What is this? It's a 3s2 p1 configuration. Yeah. So we take the p1 electron. That's the first out. The lowest energy or the highest energy, closer to zero. We take the p1 electron off. That would be that here. And for this, we need 580 kilojoules. Now the next electron, this would be the first ionization energy. The second ionization, we have the positively charged aluminum cation, and we want to rip off another electron. So now, very soon we all go home because the fire alarms go off. It's not. So that aluminum will, if it loses an electron, will be aluminum 2. But this would be now what is it? Aluminum would be a 3s2 electron. We have to take one off. And so this costs already about over 3 times as much energy than taking off the first one. Now we come to the third one. This would be then the last from the third period, the last electron, that S1, from the 3s1. And you see the Al2, I take off this last electron, I need 2,740 kilojoules. That's a whole lot more. That's 700 difference here, and this is only 580 for the first. And now I can even remove the last and a fourth one, And I need tremendous amount of energies because now I'm already what I call the orbital core. I'm at the core electrons. So I need to rip off this here, okay? This here, that would be now the 2p6. I have to take the 2p6 off. And you see how much energy you need for that because it's bound so well? 11,600 kilojoules per mole. This is successive ionization and aluminum dust. There are other ions. There are other ions that do that too. Excuse me, please. It's the smoke here. Huh?
I barely can see you. Everybody's coughing.
Okay. So let's look at the trend in ionization energies. If we go within the period, you have hydrogen. That has we already talked about this is the ionization energy. That's a 1s1 electron. We have to remove that. We made H+. Now if we go to helium, that would be the second one in the same period. Helium would be up there. So it would be a 1s2, and it would be more difficult to remove it because now we have two nuclear charges, but you have also two electrons, and they don't shield each other very well at all. Now, what would you expect if you go down now in the next period to lithium? Actually, it goes down again, because now you have the shielding of the 1s orbitals. They shield the 2s orbital, and so the effective nuclear charge, what the 2s orbital experiences, is not that large. It's smaller than what the 1s orbital experiences. And so you get, see, that's what I said, it's smaller. You see, you need only 500 kilojoules per mole to ionize this. And now what do you think if we go over to beryllium, would it go up or go down? Would go up, exactly. So that's the 2s2. And now comes an anomaly. We come to 2p1. So there's some special shielding of the 2s's to the 2p's in this case. The 2p1 has a slight dip in energy because of that. And now we go successively up to 2p2, the 2p3. So now 2p3, what is that? 2p3 is what? Nitrogen, isn't it? Okay. So far, we are parallel in spin, yeah, in the p orbitals. And now if you put it anti-parallel, you get something what is called pairing energy. That's a little bit higher level, lower energy. You need to rip off that electron. So you get a little dip here in the pairing energy when you come to 2p4. And then you go up to p5. And finally, you are in 2p6. And 2p6, your orbital is filled. Your quantum level 2 is filled. And now you have to go to the next quantum level. What do you think where the energy goes? Goes down again, and it goes nearly as far down or even further than here with the lithium. So this would be sodium 3s1. And this periodicity goes just along the whole periodic table, but it's not as pronounced as we go further out because the nuclear charge is not, the effective nuclear charge gets less and less and less. So if you look at this here, you see that's the first period. It goes up and then it goes down, up and then down, okay? Up again, next period, down. Next period, up, down, and see it goes much less pronounced, but it's still that trend. Because if you go out here, I mean, you have orbital after orbital after orbital around the nucleus, and so the effective charge is not that significant anymore as it would be here or here or here. So there's this periodicity about the first ionization energy. So you could now predict first ionization energies from what I told you, just from understanding the build-up system and the shielding of the electrons and the nucleus, the electrons and the orbitals and the shielding of the nucleus or the nuclear charge by the electrons. So this is called effective charge. Let me ask you a question. What is the ionization energy? Let me go and give you the next board here. What is the ionization energy of Cl- in kilojoules per mole? Cl- ionization energy. I want to ionize Cl-, okay? So is it, the ionization energies are here. Can you read them partially? Is it 1,251? Is that positive or negative, the ionization energy? Is it minus 349 or is it plus 349? All right, why don't you think about this and give me your answer? Ionization energy. Why don't I give you this here? 1 second. Can you read that better? Okay.
So like they would list the chlorine electron affinity as 349, not negative 349.
That's wrong.
But that's how it is in the book.
That's terrible.
But I thought that, it would be worth letting me know.
Thank you. Okay. So the book is wrong. It lists it wrong. It has the wrong sign, the book. I'll be talk about this when I have a look at that. Yeah? That's our definition here. That's how we're going to do it.
The book defines electron affinity as negative delta E for electron attachment.
Okay. And the positive for...
So they list them all as positive numbers, except
Yeah, electron affinity is negative.
well, the book lists it as positive.
Okay.
Chlorine is 349.
That's wrong. Okay? That's a definition matter. If we put in energy in at all this class, we will talk about this. But they have exothermic as negative, hopefully. Yeah? Otherwise, we give me a book, we burn it all together. Okay? All right. And there are some questions in the homework like this?
I don't know that they actually have to give numbers.
Okay. Okay, there's always a surprise, isn't it? So some author said, oh, I'm going to do it differently than everybody else. So you are ambivalent about this. No, let's not do that. See, I got out of my... So, good. Now, first of all, you need to think, in order to solve that, how did that negative charge get there? How did that negative charge get there? All right? So what kind of energy did you need or get released in order to get the negative charge there? That's the first question. Huh? You can click in then, okay? So, but now you want to remove that. So what kind of energy would you need then, and what kind of sign would that have? So why don't you discuss this and discuss it with each other and give me an answer? Another answer, some of you at least? Huh?
Like it says, if you read the chapter in the book, it says electron attachment is this. Electron affinity is defined as negative delta E.
Okay, that book is dead. Last time I used that book. That's how fast this goes with a book. They can't say anymore, they use it in Berkeley. That's what they all like to say. I don't go there. All right, let's concentrate on the question, discuss it, come on. Let's not get confused by this stuff. I defined it for you, and that's what it is today, all right? Okay, let's see what this is. Yes, this is good. So what the ionization energy has to be positive, and with this, C is right. And for the rest of you, I tell you why. So this is an ionization energy, and this is the electron affinity reaction, okay? So in order to make a Cl minus, all right, we release energy. How much real energy is released? minus 349 is released because we put in a neutral atom, we put an extra electron, and this releases energy. It's minus 349 kilojoules. Now, how much energy do I need to rip this electron off again? Plus 349. Okay, and with this was the right answer, plus 349. So let's think about that one. We have, which of the following has the smallest ionization energy? Cl minus has an extra electron, argon, and potassium plus, obviously it's missing an electron. Why don't you look at the valence electron configuration of these three ions? Just look at the valence electron configuration of the three ions and then tell me which one has the smallest ionization energy. Are we discussing this already, or discussion section already, or you guys talking about what's happening on Monday, Valentine's Day? Come on, think about it quietly. Yeah, Chinese New Year's too, so no wonder I don't get anybody to pay attention. Can you hear me in the back? Yeah, good. Okay, you can hear me okay? Good. Can you understand me? No. Yeah, that's to be expected, huh? That's why we're doing this stuff. So why don't you think about, so what's the electronic configuration of Cl minus? So this is neon filled, and now the electronic configuration is what? 3s. 3s how much? 3s2, somebody said 3. 3s2, and how many p's you have here? 3p6, okay? Now, what's the configuration of argon, pure argon, just the atom? 3s2, 3p6. What's the configuration if I have sodium plus, so I'm missing an electron? 3s2, 3p6. They are isoelectronic. They have the same electronic configuration. They are isoelectronic. But what don't they have the same? They have different nuclear charge. So now talk about it and give me the right answer, please. So they already exist in this state here. We don't care how they got there. You're filling it already, yeah? That's good. That's excellent. Now I want to hear the discussion. Come on, discuss it. Give me the right answer. It's simple, very easy. See, I see the people who come to office hour. I recognize them now. Okay. Everybody click in to get these beautiful bonus points without knowing the answer. No, all of you know it, but you just don't tell me. Makes sense, huh? Does it make sense? Who thinks it makes sense? You do? I think then if you say it makes sense, okay? That's the answer then. Yes, it is the answer. So they are isoelectronic. They all have neon-filled orbitals so that this quantum level is filled. 3s2, 3p6, 3s2, 3p6. Which one has the highest nuclear charge? Potassium. What's the second highest nuclear charge? Argon. And the lowest nuclear charge? Okay, so which one would be the easiest to remove that electron from? Okay, chlorine, because it just doesn't pull as hard, right? Good, the answer was chlorine. Now you look at here, we have here some of the ionization energies and the electron affinities. I just want to point out, you can ionize helium, but helium doesn't really like to take on any electrons, any extra electron. You can ionize, for example, neon. They're putting something in front of here now. You can ionize neon. You need a lot of energy to rip that electron off the neon because it has this very stable filled orbital configuration. That's at the end of the period. And so, but it will not, or hardly at all, will it be possible to take up an electron. And you see the trend here that I just explained to you is depicted here, and you can study this. And now we come to study this at home a little bit more, and in your book. I hope this is right in your book. And the radius of an atom we actually can't measure. You can't take a caliper and measure the radius of an atom. Even if you would have a small caliper, it's difficult to measure. So you measure compounds, the distance of molecules in compounds. And in this, for example, you measure a bromide molecule. You can do this with all kinds of different ways, with diffraction, for example. And you measure that, and you divide this, the distance from nucleus to nucleus, and you get the radius. And the radii, periodic radii in the periodic table are given here. So as you increase within the period the nuclear charge, they're pulling the electrons closer and closer. So you're getting a decrease in radius. It goes smaller. The atomic radius gets from left to right smaller. And of course, if you increase, then you go in higher and higher orbitals, higher and higher quantum states, quantum numbers. You have all those filled. Of course, you get bigger and bigger and bigger as you go down in the group. You see that here? This increases in the atomic radius and decreases from left to right. So I don't think I have time for that. Do I have time for that? Yeah, I do. Let's do this quickly. Which of the following, can you read this here? Yeah. Which of the following has the smallest radius, and I mean the atomic radius? Chlorine, argon, or potassium? Chlorine, argon, or potassium? Okay, give me a quick answer on that because I have a nice experiment for you. From left to right, smaller. From top to bottom, larger. But then when you go on below, it gets smaller again. But not as small than the period above. Because you're adding now higher level orbitals. Okay. Answer quickly that I can give you the points and explain it to you because we are ready? Almost ready. I don't want to have Karen pull out this whole experiment again. All right. I think we have enough time. Always this time pressure. Okay. Let's see if you can vote with the majority. Yes, you guys are right, and this is good. So it is B, of course, I told you. So, come on. So what was that? Chlorine, argon, and potassium. Chlorine is here. This is a 3s, 3s2, 3p5, 3s2, 3p6. So it has an extra nuclear charge. It pulls more on that charge. So it is this is larger than this here. This is very small. Now in this one here, this is larger than both of them here. It's in the next period. It's right here. See that? Potassium. Okay? So the answer was, oh yeah, right, argon. Good. Let's do an experiment. Let's do some, remember we had some exotherm, that must be an exotherm experiment, releasing energy. Give me 3 minutes, it's worth it. So we have hydrogen gas and chlorine gas, and now we're coming into binding. Like in our first lecture where we bound hydrogen and oxygen to water, we're making now HCl, hydrochloride, okay? Hydrochloride in gas form. And what we have here, if I could have the picture, we have here I get a pointer or something. Here, that's a pointer, okay? We have here, we had this filled with water here. You see that? We had this filled with water. And now Karen has put in chlorine gas and hydrogen gas, a mixture of chlorine gas and hydrogen gas. And so you know nothing is happening because we need the activation energy. And so I have energy right here, green energy, not the green. Green is very fashionable at the moment. We have green energy, so I'm going to point this at it. E equals H times nu. I'm going to point this at it. Are you ready? I'm going to point this at it and start the reaction. Let's see. Nothing happens. So what do? I need some, what? More energy. What kind of color would I use? Okay, I use a blue laser, since you say it. So we have a blue laser here. And I want to show you that there's really a blue laser here. You see that here? A blue laser? All right. So, we have pointed that blue laser. Can we have the overall picture maybe? Or shall we? Yeah, we have pointed that blue laser at our reaction. And we adjusted it. And so what I will do now, I'm going to use my hand here. I think I put it here. I'm going to use my hand. And I'm blocking the laser. Are you ready? Why don't we count it down? 3, 2, 1, 0. Ignition. Okay. Happy holiday. See you on Wednesday. And now if you look at it, you can see, he shut it off. There's some gas in there, which is hydrochloride, HCl gas.